All right, let's take a few minutes to review some of the concepts from the early section of the chapter, 7.1 through 7.3. It's been a while since we looked at those, and those will be on the exam. First of all, 7.1, we talked about operations and composition. Operations include just adding functions together, subtracting them from each other, multiplying and dividing. And then composition is a little bit trickier. It's where you evaluate one function and take the result of that and put that into an additional function. So on the right, if you want to look at, on the right, f of g of x, you're going to say it the same way, f of g of x, f of g of x. And the idea is you want to start on the inside the parentheses and work your way out. So you're going to evaluate g of x first, and then take that value and evaluate f. So when you're looking at this function, you start with the g of x, and then you plug that result into f. So it's like you go from right to left when you're dealing with composition. Of course, order does matter with this. So here's an example. We've got two functions. Now we're going to do some fractional exponents since we're able to do that. Let's go ahead and try putting together combinations. So pause the video, try to work out f plus g of x, add the functions together, subtract them, and then do the composition in the second part. And then I will reveal results and see how you do. Okay, so go ahead and pause and work those out. Okay, we're back. So f plus g of x, you have two different fractional exponents, and they have the same base but different exponents, so you can't really add them together. So you have to leave them just as they are, x to the 1/3 plus x to the 1/4. Same thing with subtracting, you can't simplify that any further. Now multiplying, you can. When you're multiplying exponents with different fractional exponents, you have to get common denominators, because remember, when you're multiplying, you add those exponents. So 1/3 plus 1/4, get those into common denominators, you get x to the 7/12. F divided by g is x to the 1/3 divided by x to the 1/4, or x to the 1/3 times x to the minus 1/4. Remember, when you have a fractional, when you have an exponent in the denominator, you can move it to the numerator and make that exponent negative. So that's what it did, x to the 1/3 times x to the negative 1/4. Again, I need those to be common denominators so I can add those fractions, and I end up with x to the 1/12. Okay, then we go to composition over here on the right. You're going to take g of x, which is x to the 1/4, and plug it in to f of x, or x to the 1/3. So when you get x to the 1/4 raised to the 1/3. Remember, when you take a power, an exponent, and you raise it to another one, then you multiply the exponent. So 1/4 times 1/3 is 1/12. By the same token, you take f of x, which is x to the 1/3, and plug it into g of x, and you're going to get that raised to the 1/4. You multiply it, you're going to get the same result. So in this particular case, you get the same result either way, but that's not typical that it's commutative, because the order definitely matters. But in this case, it looks like it's okay. Okay, another example, operations and composition. Pause the video, work out these examples, and then I will reveal the answers. All right, go ahead and pause the video, check your answers, make sure you got it right. I think this one is pretty straightforward, at least in the adding the operations. Just remember, I guess the one thing to make sure you pay attention to is the notation, f plus g of 7. That's not saying take the function f and the function g and multiply it by 7. It's saying evaluate f at 7, evaluate g at 7, and add them together. I know there was some confusion on the last quiz when people thought that meant multiply by 7, and it does not. It means evaluate those functions at that value. Same thing over here on the right. F of g of 2 is first evaluate g at 2, and then take that result and evaluate f at that value. Okay, so hopefully you understand this stuff. I'm going to move on. 7.2 is functions and their inverses. So in the first case, finding an inverse, if you have a set of ordered pairs, all you have to do is basically switch the domain and the range values. So switch the x, switch the y, and you'll get 6, 3 in the first one, -4, 2 in the second, and 7, -4 in the third. So that one's pretty straightforward. You're just switching the x and y values when you're finding your inverse. Now in the case of a function, what you want to first do is write the function again as a y equals instead of g of x. So you get y equals the square root of 1/3 x plus 3. And then you've got to try to solve for x and get it in terms of y. So, first you've got to switch the x and y and then solve for y. Okay, so we switch the x and y. Now I got to solve for y. So I'm going to have to square both sides. I'll get x squared is 1/3 y plus 3. X squared minus 3 is 1/3 y. Multiply both sides by 3. Y is 3x squared minus 3, or 3x squared minus 9. And that would be your inverse. When you graph the inverse function, let me pause. When you graph the inverse function, it will be a reflection over the line y equals x. So, that's not what I want to do. If you have a line here and you have some function, if you have some function that looks like this, let's see if it goes like that, then the reflection over the axis would look something like that. So that would be the inverse function. Okay. Using composition to prove inverses. This is what you guys were supposed to do on your quiz, and a lot of people didn't do it very well. So what you want to do is you find the composition of both ways, f of g of x and g of f of x, and show that they're both equal to x. And if they are, then you have inverses. So let's give this a try. F of g of x, I'm going to take g of x, 1/2 x minus 1, and I'm going to plug it into the function f. Okay? And I'm going to see what I get. So, I'll do f of g of x first. I'll take 2 times the function 1/2 x minus 1 plus 1, and then I'm going to simplify that. My 2's cancel. I got x minus 1 plus 1, which is x. Hooray! So that one worked. Let's try the other one. G of f of x. Now I'm going to take f of x, a function 2x plus 1, and stick it in where I see an x in g of x. So it should look like this. 1/2 times 2x plus 1 minus 1. Simplify that. 1/2 times 2x, which is x. It checks. So that shows you that these two functions are in fact inverses. Again, you do the composition of both sides, and you you see what they equal. If they both equal x, then you know you have inverses. Square root functions. Okay, the key with square root functions is to remember your just general rules of transformations, moving things up, moving things over, and then also really understanding that you need to restrict the domain. So whatever is underneath the radical, that has to be greater than or equal to 0. So that's going to allow you to figure out the end point of your domain. So x minus 2 has got to be 0, greater than 0, so x has got to be greater than or equal to 2. So your domain is going to be all real numbers greater than 2. And that plus 5 on the outside means you're going to take the whole thing, the original parent function, and slide it up 5. That minus 2 means you can take the whole thing and slide it over to the right 2. And the range, because you've slid it up, is going to be all real numbers greater than 5. Another way to check that, or to know that, is when you first test this domain and you get this value for x is greater than or equal to 2, plug that value back into the function and see what you get for y. And if you do that, you're going to get y equals 2 times, now I'm going to plug in 2 minus 2 is 0, times 0 plus 5. So there is my y value that's going to be the bottom level that sets up the range. So you can always go back and find the y value if you're looking for that kind of end point that determines the beginning of your function. When you're graphing, you can use the transformations to help you figure out kind of where the graph is going to go. But in general, it's always a good idea to just pick some points and plot them, and use your calculator, or pick points that give you perfect squares so it's easier to graph. But that's just kind of hardcore, tedious work. You got to do it though. Okay. Nth roots. So when you're looking for nth roots, not square roots, but cube roots or fourth roots or something like that, then what you want to do is take what's under the radical and break it down into its most simple base form. In other words, take it, factor it, and write it as exponents, and see what you end up with, and then pull out any perfect, in this case, perfect fourths, and then leave behind what you have to. So when I factor this 128, I don't know. That's 2 to some power, I think, but I don't know what. So I just start dividing by 2 and see what I end up with. Well, it turns out I end up with 2 to the 7th power. I want the fourth root of that, so that's going to be 2 to the 4th times 2 cubed. So since I have a 2 to the 4th, a perfect fourth, I can pull that 2 out, and I'm left behind with the 2 cubed. Okay. And then the next one, cube root of 54, x cubed y to the 10th. Go ahead and try to do that one, and then I will reveal the results. So pause it and work that one out. Okay. So in that case, I'm looking for perfect cubes. 3 is a perfect cube. I can pull that out. And then I've got an x cubed in there, so I can pull that out. And then I've got 3 y cubes, or y cubed to the 3rd power, y to the 9th. So I can pull out a y cubed. And then I'm left behind with the 2 and the y. They're stuck in under the radical. And remember, it's a cube root and not a square root. And that concludes our review.